Welcome to Module 4. Having explored how AI helps machines see, now we turn our attention to how they understand, interpret, and generate human language. This field is called natural language processing, or NLP. Human language is incredibly complex. It's filled with ambiguity, context, nuances, sarcasm, and cultural references. For a machine to truly understand what we say or write, it needs to go far beyond simple keyword matching. NLP aims to bridge this gap between human communication and computer comprehension. Think about the challenges. A single word can have multiple meanings depending on context, like bank, riverbank versus financial bank. Sentences can be grammatically correct but semantically nonsensical. Slang, idioms, and accents add even more layers of complexity. NLP tackles these challenges using a blend of computational linguistics, statistics, and increasingly deep learning. The applications of NLP are everywhere in our daily lives, from the spell checkers and grammar correctors you use to the spam filters protecting your inbox, the chatbots answering your customer service questions, and the language translation apps connecting the world. NLP is a silent enabler of many modern technologies. In this module, we'll start by understanding how unstructured text is converted into a format machines can process. Then we'll explore core NLP tasks, and finally dive into the revolutionary transformer architecture, which underpins the latest advancements in language AI, including generative AI. Let's begin by looking at text representation. Computers understand numbers, not words, so the first challenge in NLP is converting human language, unstructured text, into a numerical format that machine learning models can process. This lecture covers key text representation techniques. The simplest approach is the bag of words model, or BOW model. Imagine a sentence. The cat sat on the mat. We create a vocabulary of all unique words. For each sentence, we count the occurrences of each word. The order of words is ignored, hence bag of words. While simple, it loses word order and semantic meaning, but can be effective for basic text classification. Building on BOW, TF-IDF, or term frequency inverse document frequency, assigns weights to words based on their importance. Term frequency, TF, is how often a word appears in a document. Inverse document frequency, IDF, measures how rare a word is across all documents. Words that appear frequently in a specific document but rarely across the entire corpus get a higher TF-IDF score, indicating their unique importance to that document. While BOW and TF-IDF are useful, they suffer from a major drawback. They don't capture semantic relationships between words. For example, king and queen are related, but these models treat them as completely separate entities. This led to the development of word embeddings. Word embeddings are dense, low-dimensional vector representations of words. The key idea is that words with similar meanings will have similar vector representations and will be positioned close to each other in a multi-dimensional space. These vectors are learned from large text corpora. A groundbreaking embedding technique was word-to-vec, which learns word embeddings by predicting words from their context, or vice versa. This revealed fascinating properties like being able to perform vector arithmetic. For example, vector of king minus vector of man plus vector of woman often results in a vector very close to vector of queen. Another popular embedding is GLOVE, or Global Vectors for Word Representation, which combines global matrix factorization and local context window methods. Word embeddings provide a much richer and more nuanced representation of language, allowing models to understand semantic similarity and relationships between words. This was a crucial step towards more sophisticated NLP models. Now, let's look at some common NLP tasks. With text now represented numerically, we can perform various NLP tasks. Two of the most common and practical are sentiment analysis and general text classification. Sentiment analysis is about determining the emotional tone of a piece of text. Is it positive, negative, or neutral? Or perhaps it expresses anger, joy, or sadness. It's widely used for understanding customer feedback, social media monitoring, and brand reputation management. For example, a review saying, "This product is amazing, I love it," would be classified as positive. "The service was terrible and slow" would be negative. Challenges include sarcasm, irony, and nuanced language. Models are trained on large datasets of text labeled with their sentiment. Text classification is a broader category where the goal is to assign predefined categories or labels to text. Sentiment analysis is a specific type of text classification. For example, categories are positive, negative, neutral. Other examples of text classification include spam detection, categorizing emails as spam or ham, topic categorization, assigning news articles to sports, politics, entertainment, or urgency detection in customer support tickets, example, high, medium, or low. The process typically involves text pre-processing, cleaning text, removing punctuation, lowercasing, tokenization, feature extraction, converting text to numerical representations, both TF-IDF, or more commonly, word embeddings. Model training, using a classification algorithm, logistic regression, SVMs, or deep learning models like CNNs or RNNs trained on sequences of word embeddings to learn from labeled data. Prediction, classifying new, unseen text. Both sentiment analysis and general text classification are powerful tools for extracting insights from vast amounts of unstructured text data, automating processes, and enhancing decision-making. Next, we'll explore more advanced sequence models. Many NLP problems involve converting one sequence into another, translating a sentence, summarizing a document, or generating a response. This is the domain of sequence-to-sequence models, and a critical component within them is the attention mechanism. A basic sequence-to-sequence model consists of two main parts, an encoder and a decoder, both typically built using RNNs or LSTMs. The encoder reads the input sequence, example, an English sentence, word by word, and processes it to capture its meaning into a fixed-size context vector or thought vector. Once the encoder has processed the entire input, this context vector is passed to the decoder. The decoder then takes this context vector and generates the output sequence, example, the French translation, word by word, predicting one word at a time until an end-of-sequence token is generated. While effective for shorter sequences, a major limitation of this basic sequence-to-sequence architecture is that the entire input sequence must be compressed into a single fixed-size context vector. For long sentences, this bottleneck can lead to information loss, especially for early parts of the input. This is where the revolutionary attention mechanism comes in. Instead of forcing the encoder to compress everything into one vector, attention allows the decoder to look back at different parts of the input sequence at each step of generating the output. It essentially weighs the importance of different parts of the input when generating each word of the output. Imagine translating "the cat sat on the mat." When the decoder translates mat, it pays more attention to the words cat and sat in the original sentence. Attention calculates a score for how relevant each encoder hidden state is to the current decoder hidden state, then creates a weighted sum of those encoder states to form a new context vector for the decoder. This dynamic access to the entire input sequence, rather than just a single fixed context vector, allows sequence-to-sequence models with attention to handle much longer sentences and achieve significantly better performance in tasks like machine translation, text summarization, and question answering. The attention mechanism was a game changer in NLP, addressing the long-term dependency problem more effectively than LSTMs alone. It paved the way for even more powerful architectures, which we'll discuss next. The transformers. The attention mechanism we just discussed was so revolutionary that it led to a completely new architecture that transformed NLP, the transformer. This is the foundational model behind all modern large language models. The paper, Attention is All You Need, introduced the transformer in 2017. What made it so revolutionary? It entirely ditched recurrent neural networks, RNNs, and LSTMs. Instead, it relies solely on the attention mechanism, specifically a variant called self-attention. Traditional RNNs process sequences word by word sequentially. This makes them slow to train on very long sequences and difficult to parallelize. Transformers, on the other hand, can process all words in a sequence simultaneously. This parallelization capability was a massive breakthrough, allowing for training on vastly larger datasets and longer sequences. The core of the transformer is the self-attention mechanism. In self-attention, each word in an input sequence learns how much it should attend to or weigh every other word in the same sequence. For example, in the sentence, "The animal didn't cross the street because it was too tired," self-attention helps the model understand that "it" refers to animal by calculating attention scores between it and every other word. This ability to model relationships between all words in a sequence, regardless of their distance, is what gives transformers their power. It allows them to capture long-range dependencies and complex contextual nuances much more effectively than previous architectures. The transformer also incorporates positional encoding to inject information about the relative or absolute position of words as it lacks recurrence. The transformer architecture, with its reliance on self-attention and parallel processing, unlocked the era of truly massive language models and became the backbone for systems like GPT-3, BERT, and countless others. Understanding it is key to grasping modern generative AI, which is our next major topic. But first, let's look at some NLP case studies. Natural language processing is no longer just for researchers. It's deeply integrated into the products and services we use daily. Let's explore 5 key case studies where NLP has made a significant impact. Case study 1, Google Search and Ranking. Every time you type a query into Google, advanced NLP algorithms are at work. They understand the intent behind your query, identify relevant keywords, and rank billions of web pages based on their relevance and authority, providing you with the most useful search results. Case study 2, Chatbots and Virtual Assistants. From customer service chatbots on websites to personal assistants like Siri and Alexa, NLP enables these systems to understand your questions, process your commands, and generate coherent, helpful responses, often in real time. This automates support and provides instant information. Case study 3, Spam and Phishing Detection. Before an email even hits your inbox, NLP models analyze its content, sender, and structure to identify and filter out unwanted spam or malicious phishing attempts, protecting users from scams and junk mail. Case study 4, Content Moderation on Social Media. With billions of posts daily, social media platforms use NLP to automatically detect and flag harmful content, hate speech, misinformation, or violent extremism, helping to maintain safe online communities. Case study 5, Grammatical Error Correction and Writing Assistance. Tools like Grammarly or built-in word processor features use sophisticated NLP to identify grammatical errors, suggest stylistic improvements, and even rephrase sentences for clarity, significantly enhancing writing quality and productivity. These cases demonstrate NLP's fundamental role in making technology more intuitive, intelligent, and useful for communicating with and understanding human language. And with the transformer, we're now at the doorstep of something even more extraordinary: generative AI.